I need to now transition to the Linux security model. And this is the security course. So I needed all that other stuff in order to talk about Linux security. And specifically, I'm going to start with Linux access control. And we'll go through just some of the basics. If you recall up front, that very first week, we talked about what access control models do. So the operating system kernel, when you have an access control policy, it's up for the kernel to basically enforce whatever policy you have specified for your system. And that's done with a reference monitor. So this is a picture. You have some users on the left, some subjects, and they're trying to get access to objects, which are on the right. And there's some kind of policy and some kind of permissions that are specified with that policy that this reference monitor, which is in the Linux kernel, is going to enforce. So that's the general picture of this. So on Linux, we're just going to cover the default access control model for Linux, what Linux ships with when you download it and install it on your machine. It's important to note that this isn't the only security model that you could install for Linux. One of the things that the federal government was interested in was using the code base of Linux, but using it in a much higher security environment. And this is what this SE Linux project was intending to support, to bring your own access control models into your computing code base. And so this is all configurable, but I don't have time to cover all the different SE Linux modules for doing all these different access control models. You're going to definitely run into the default one, especially if you're like a developer dealing with like containers and virtual machines that you're deploying. Almost everyone in industry is using the default one. So that's what I'm teaching you. But just know that there's other ones out there that you can come across. Okay, so I'm going to rewind back to the different parts of an access control model. And those are subjects, objects, operations, and policies that you would define for your system to control the security. So Linux subjects, we'll start with the first one. The subjects in Linux are basically users and groups that are local to the operating system. So with Linux users, the users are associated with a unique integer, and that's their UID. And you'll see the UID terminology all over the place with Linux. There is a special UID of 0, and that's for the super user. That's for the root account. Moreover, the low integers are typically reserved for system processes, for compartmentalizing the different system processes as their own user. And you'll see when we talk about Android, Android takes this further. Every application gets its own UID in Android. They want clear isolation and separation of these applications via the UID, because Android is Linux underneath mostly. Okay, the human users that you would configure on a Linux system would typically start at UID 1000. So if you download Linux, you install it, and then you do a user add, typically that first user is at like 1000 or 1001. It's just trivia. The other thing that Linux supports is a notion of groups, because eventually you want to be able to express a more flexible security model. Like if you want to share a file with someone else on the Linux system, you don't want to give them your UID, or you don't want to have to email that thing to them all the time. You actually want to be able to do something a little bit more direct, and that's with the Unix group, with the Linux groups. So these are sets of users associated with a group identification integer, so a GID, and then you're able to add and remove people from that GID to do the sharing. So that's the idea. So this is basically going to allow us to have multiple users to share the same files. And this is different than having a file that only one person can see or having a file that everyone can see. So this gives you somewhere in between. Okay. A user can belong to many different groups. And this is, again, to support the flexibility of file sharing under different contexts. at a given moment in time, only one group is active for a particular user. A primary group is activated. And so one of the nice things about groups is that it allows a user to acquire and drop privileges based on what the user is trying to do on the system. It can activate different groups. Okay, so each file and running process is owned by exactly one UID and belongs to one GID at a time. Okay. The information about UIDs is specified in a file on the system called etc password. So in etc, all the system configuration stuff is in that directory. Etc password has this file that contains all the UIDs and default GIDs for all the users on the system. This is what it looks like. So it's a colon separated file. And these are the parts of it. So this is the user login name is the first field. The second field should be an X all the time. It used to contain the password hash of the user. And so almost all the time, whenever you see an X, it means that the password hash can be found in a shadow file somewhere else. And we'll talk about that in the next slide. The UID is the next one. So that's the integer we just talked about. The default GID or the primary GID for that user is the next field. Now on Linux, when you create a user, it automatically creates a group for you with the same integer. So that's why this is exactly the same as the UID. And then it gives you the user's home directory. Where's where does that user get dropped into when they log into the system? And then the default shell for the user. So those are the pieces of etc password. Now, originally, this file was readable by everybody, and it stored password hashes. And so that's not good. Like, why do you want to give everyone the ability to read password hashes? Well, that was what the default setting was. And so to address this, we realized that many programs and many people need access to some of the information in this etc password file, but only the login process really should be accessing this hash to verify that the password was entered correctly. And so as a result of this, the password hash got moved somewhere else, and that somewhere else is in this etc shadow file. And so this is a file that's typically used to store all the password hashes for all of the users on that system, and it's only readable. The intent is only to make that thing readable by the login process, the thing that's actually checking the password hashes. So here's an example of an etc shadow entry. And so it's colon separated as well. And so it's got the user login name, and this is the same name as an etc password. And then it's got this password hash. And at the beginning, you'll see this dollar integer dollar. This gives you a format hint for the hash, because there's actually a whole bunch of different password hashing mechanisms that Linux supports based on the strength of the password hash you want to deploy. So like they'll find a weakness in a password hash and they'll develop a new algorithm, but then they need to store the fact that they're using a new algorithm in the hash itself. And so it's stored in line. So the algorithm, this is, I think, MD5, which is not something you want to see in an etc shadow file, actually. But like, this is basically the kind of password hash and then the hash itself. The other thing that it stores is the date that the password was last changed. And this is given an absolute number of days from the epoch from 1970. So it could be a large integer. In this case, I just for brevity, made it a short integer. The last two are the minimum number of days between password changes and the maximum number of days between password changes. Now, this is a really primitive way of specifying a password policy. And so this is not used very often at all. In fact, this is typically one of the first things that you would ignore on a Linux system is this thing. There are other ways of defining password policies. So some password policies are like, has to have a number or a letter, has to be changed every 6 months. So there's a rich kind of way of defining password policies. This ain't it. And so this is, you typically do a different, we'll talk about password authentication plugins, but this would be replaced. Almost all the time, this is replaced with something else. But since you see it in the file, I'm going to explain it to you anyway. So we talked about groups. The group mappings are defined in this file, etc group, and it specifies all the groups that particular users are members of. And it also, when you create a new user, it actually defines your primary group ID, that GID for that user, in this file as well by default. There are special groups, and all those GIDs under 1,000, just like the UIDs under 1,000, are kind of reserved for system groups. Some of the ones that you might find, we talked about www data as a special group for web servers. There's a sudo group for regular users who we are allowing super user privileges temporarily to execute administrative tasks. So that's in the sudo group. And then Docker. So Docker, if you allow a user to run Docker containers on your system, Docker actually requires elevated privileges to run. This is why you can't run a Docker container in a Linux lab machine, because you could basically own the box that it's on. And so only special people are allowed to run containers, and that's done with this with special group. So you'll peek into this file and you see there's the group name on the left, and then the group ID is followed by, is here, and then the different people that are associated with each of these groups. Okay, so with Linux, there are two types of ownerships. And they're basically mapped into those subjects. So both users and groups can be associated with files and directories as their quote unquote owner. With this ownership, you can have files and directories define access based on the ownership level. And so there is the user ownership permission. So what permissions does the owner get on this particular file? There's also a group set of permissions. What privileges does someone in the group get for this particular file? And then there's the everyone else access. If you're not a group owner or the owner itself, what access do you get on this particular file? So that's denoted by U, G, and O when we're using the permission commands in Linux. Okay. So those are the subjects. We're now going to talk about the objects, the operations, and the policies. The objects are really easy because Unix has said everything's a file. So everything is associated with a file, and like everything that you want to protect is associated with a file. So it's all done uniformly. So that's nice. And then when you want to define operations on objects, these policies also are associated with the file. So in terms of the different operations that Linux allows, there are three. There's the read access, the write access to that file, and then there's this execute permission. And execute has two different semantics based on the kind of file you associate that bit with. If it's a regular file, that means a user, group, or other people can invoke it, can execute that particular binary. If it's a directory, it means that the user, group, or other person can change into it. So, I guess you can kind of see that as being executing the directory by entering the directory, but that's what it means. The policies. The policies are set by the owner of the file. The owner is going to say, hey, these are the permissions I want to allow on the object that I just created. And so this gives this is basically what a discretionary access control model is. The owner has the discretion to set the policy on that file. The permission bits, the permissions that the owner defines, those are attached to each file. It's done on a file by file basis. And so if you look at this in our definitions, this is discretionary access control, where the permissions are stored as access control lists attached to the resource. So this is important. I put a star here because if this was to show up on an exam, or if I were to study for an exam, I would like look at this as being something I would ask, because you should know this. How is it storing the permissions? And then who gets to assign those? Well, that's these two things. Okay, so with permissions, they're often associated with letters. So read is R, write is W, execute is X, and they're organized as bits. It's like a bit vector associated with a file. And so with that, they're often stored as a bit vector, with the most significant bit being the read bit and the least significant bit being the execute bit. And when you store these as a bit vector, you can refer to these triplets in octal format, right? So because there are 3 bits, you can store these as numbers 0 through 7. And so that's the shorthand for when you're specifying permissions in these permission commands that we'll use in a second here. Okay. So now we have the permissions and we have the subject types that they apply to. So we have 3 subject types, user, group, and other. We have 3 sets of permissions for each one of those subject types. So this is what we have when we do a listing on a file. We have these permission triplets. We have, when you do this ls minus L, you see these 9 bits. Here, there's the file type, which is the first letter, and then you see the permission bits that follow this. And that's basically the user attributes are on the left. So these are the user permissions. The group permissions are in the middle, and then the other attributes are on the right. So in this case, for this particular directory, the user can read, write, and change into this directory. The group, so anyone associated with the www data group can read the directory and change into it. And then anyone else can't read it and can't change into that directory. Okay, are there any questions about permissions in Linux and how it works?
Say some permission is assigned to a directory and another file is placed inside that directory. So does it by default get the permissions which are assigned to the directory?
Oh, we'll get to how that's set by default. That's a really good question though, because gosh, when I create a file in Unix, I'm not changing the permissions at all. How many of you actually create a file and then change the permissions as the next thing you do after you create the file? No one does that, right? At least I don't. Maybe some of you, but this is stuff that you're not even thinking about. You're just using Linux, right? And this is a problem. If everyone is just using Linux and not understanding all the things being protected, this is why we have so many security problems. And so this is why, you now mindfully knowing this can be an issue, hopefully you can figure out your permissions before you deploy something and get it owned. Okay, so I'm going to go all the way back. Well, not all the way back. I'm going to go back to the Etsy password example. We wanted people to read Etsy password, but we moved all the password hashes somewhere else so that only the login process can read those password hashes. And so on any Linux system, if you do an ls-l of Etsy shadow and Etsy password, you see Etsy password is readable by everybody, right? So it's readable and writable by root. If you're in the root group, it's readable. And if you're anyone else, you can read that file too. So that's completely open because you need to be able to read different users in order to add users to if you yourself want to add group permissions and you want to see what the GID of users are, you need access to that file. But if you look, Etsy shadow, it's readable by root, readable and writable by root, and it's only readable by people in the shadow group. Okay, so you have to belong into the shadow group to get access to the Etsy shadow. Everyone else does not get access to that file. So this is why if you log into a Linux lab machine, you can't get cat Etsy shadow should not work. So you're not able to see anyone else's password hash on this system, which is a good thing. So this will come up if you want to do a Linux system administration certification exam, which is basically a security certification. They'll ask you, hey, say I'm an adversary and I get on a system. It's I want to run a dictionary attack. I want to get access to the Etsy shadow file so I can run a dictionary attack on the password hashes. And so this particular exam question is like, do I need root access to do this? And the answer is, you want the answer? No, but the answer is all I need to be is a member of the shadow group. I need to find a way to be on the shadow group, and then I can get access to this file without being root. So that would be the answer to this. Okay, and you'll be actually in your labs, you'll be cracking a whole bunch of password hashes. So if you do get access to the Etsy shadow file, you can start logging in as all kinds of users on this if they have used any of the passwords that show up in like the rocku.txt file. So that's why I had you like look at that file, because those are all credentials that people have used. And so if you can generate all those hashes for all of those passwords, then you can see if it shows up in any hash that you obtain if you've gotten access to the Etsy shadow file, which is a scenario we'll do.
Do they get a little harder with like salts?
Yeah, we'll get to that. How do you store, like, so the strength of the password hash is gonna matter. And we're gonna, actually, that's part of your lab too. Like, can I figure out what is the best password hash to use that is gonna prevent someone from, so if someone gets Etsy shadow, how do I make it difficult for that person to crack passwords? We'll get to that. That's next week when we're doing the crypto part of this class. Okay, so let's talk about permissions and paths, because we had this question about, well, what about a file in a directory? How is that managed? So when you are on Linux and you are trying to list a directory, you need read access to that directory in order to list the files inside of it. That makes sense, right? Like the directory is just another file, and that file's got the entries, the inodes of the files in that directory. So you need read access to the directory in order to get all the inodes. And so here's an example. I am myself on this machine, and I look at two directories. I say, well, let me look at my home directory, and I have read, write, and execute access to this. And then I look at someone else's directory, just a directory entry. So I do an ls-ld of some guest account, and it appears here that because let's say I'm not part of the guest group, it appears here that I just have execute access to this directory. Actually, it doesn't even matter if I'm in the guest group. Well, I'm definitely not the guest. So I don't have read, write, and execute to this user's home directory. I only have execute for this home directory. If I try and do an ls of that directory, a straight up listing, and so this is where that bang dollar syntax that I referred to like last week, I use this a lot because if I do an ls-ld of this, and then I do an ls of bang dollar, it just gets the last argument of this. So now I'm gonna try and do a read listing of this directory, and this will be can't open that directory, permission denied, because I don't have read access to it. Now I have execute access to this. Why would you ever give someone execute access without read access? And so as it turns out, if you just want to change into a directory, all you need is execute access. You don't need read access. So I can actually cd into this directory. And in this directory, if there is a directory that I already know exists within this directory, say like the public HTML directory, which is everyone's default web page on a lot of these web server distributions, then you can actually perform a listing on files that you know exist. And of course, here it says public HTML is a directory inside of home guest, and that also has just execute bits for the others. And so now I can actually change into that directory too. So to read any file, you have to have execute permissions all the way down to that file, and then you have to have read access to the file itself. And this is how home directories and in web servers are sometimes done. So if you want to serve your home page out of your home directory in public HTML, but you don't want users to be able to list your home directory, then what you would do is you would just give execute permissions all the way down to your to your public HTML. You would take out the read permissions, and then just underneath public HTML, then your files can be openly readable by everybody in order to serve a web page from. And so if I am all the way down here, so you see I'm someone else, I've changed into guests, home guest public HTML, and then I see this file index.html here because I know that this is the default web page of most users. I can actually do this as myself. And this is how I can read someone's web pages without getting full access to their home directory, which I don't want. This is just one way of doing access control on the Linux system. Okay, question.
Why didn't the thing $sign with the LS?
So this, I don't have read access to list the contents of home guest. This I can do because /home, it turns out I have read access to /home, so I can actually get this information out of /home. But when I try and list this thing directly, I can't actually go and open that file. Yeah.
So you can't list the files in the directory, but if you know a file is in that directory, then you can.
Yeah, that's the trick here. And I don't know if you'll ever come across that, but that's how web pages were initially done on web servers. And in fact, as far back as maybe like they made that change 3 years ago to pull it out of the user's home directory because people weren't able to configure this. People were actually taking their home directory and making it readable to everyone in order to put their readable web page in public HTML. They thought they needed to open up readable access rather than just opening up executable access. Cat, I think, just gave up. They're like, people are just opening up their directories rather than doing this, so that we might as well just go to a different way of storing user web pages. How many of you store your user web page in MKEX? You do? Okay, so did you have to move your stuff around when they did that or no?
If I changed the permissions, but I know every student does still have a public HTML folder that you can.
Oh, okay, so maybe they didn't change it then. I thought they did. I got a message that I ignored, but I thought it was. I thought they were making some changes to public HTML to get it out of their user directories. Okay, so there are some special permission bits. I said they were permission triplets, but I kind of lied. Just out of simplicity, I was like, okay, just focus on those bits. Those are the main bits. But there are these corner cases that Linux has and Unix has. And one of these corner cases is this sticky permission bit. So that's the T bit. And this is associated only with directories. And it's most commonly associated with /temp, which is a temporary directory shared by everybody on the system. And so the idea of the sticky bit is that you want to make files in the directory stick to the users that created it. So if I create a file in /temp, I don't want you to turn around and be able to, like some other user, to be able to turn around and delete that file. I was kind of using that file. I don't want you to delete it out from under me. But there are no protections otherwise, because /temp as a directory is completely open. Anybody can read, write, or do anything in that directory, and that's intentional, right? And so the idea is I have this wide open directory that anyone can write to. I actually do want to prevent users from deleting each other's files in that directory. That's what the sticky bit is. So with the sticky bit, the files cannot be removed in this directory or renamed unless by the owner of the file itself. So if guest creates a file in /temp, only the guest user can delete that file. The other person who can remove or rename files is the owner of the sticky directory itself. And in this case, /temp is owned by root. Okay, so here's an example. I am myself. I list this directory /temp, and you see this is read, write, and execute for everybody, and it's sticky. That's where the T bit comes from. So this directory has this sticky permission bit set. The owner is root of this directory. And if I do a listing, because this is completely wide open, I list this file in /temp, and this is owned by the guest user. So if I try and remove this, I am going to get a permission denied, right? Operation not permitted, because I'm neither guest nor root in this case. Are there questions about the sticky bit? Again, this is just kind of trivia, but I think this actually does show up on Linux system administration exams too. Yep. Yeah, so we'll talk about, in fact, this. You could use change mod, but I'm not going to give you the command. Like, I think it would be rare, but like, yeah, you would do a +T instead of a read, write, execute. You could do a T. Yep.
If you own if you're root of a folder, and then there can't be folders in there that you can't read.
You can list the entries. So as the owner of a directory, you can list everything that's in that directory file, which is all the inodes. But like you might not be able to cat a file. You wouldn't be able to read a file unless you have the permissions to that file. So that's like I could own, like, say I create a directory and it's readable, writable by everybody, and someone goes in there and creates a file, but then turns off the other and the group permissions on that file. I can see that the entry is in my directory because I own the directory, but I wouldn't be able to access that file itself because there's two files there. Yeah, there's a directory file that lists it, and then there's actually when I want to open that file up, those are two different operations. Yep. Okay, so eventually you're going to want to change the permissions on these files, and that's what chmod does. This will allow you to configure these permissions. There are two ways to run this command. There is a relative mode and an absolute mode. The relative mode is the easiest to think about because you're going to say, well, what kind of subject permissions do I want to change? The user, the group, or the other access? And that's UG and O. I can also say I want to change the permissions across all of them to be the same thing. And that's what the little a is shorthand for. And then I'm going to say I'm going to either add or subtract one of these permission triplets from access to that file. And then I give the file name. So here's an example. I do a listing of this particular file, and I see that I'm the owner, and I only have read write for the owner of this file. And then I want to allow people in the www data group to read this file. And so I say add to the group permissions, read access to this file. And then when I do a listing of this file again, you'll see that this bit has been set. And now people from www data can read this particular file. I do another listing and say the current directory that I'm in has wide open access. So everybody can read, write, and execute in this file. And I was like, you know what? I trust www data, the people in that group, to do the read, write, and execute, but I no longer want everyone else, the others, to do the same thing. And so I can do a change mod others, and I can subtract all of these permissions on the current directory. And then when I do a listing of this, you can see those permissions are now taken away. And then other people don't have access to this particular directory. Yeah.
It's probably covered already, but how do you change what group is being?
No, it hasn't been covered, but yeah, it will be covered. Yeah, that's I think that's after change mod. I'll do a change own in the change group. Yeah, because you're like, well, I didn't mean for it to be created with the www data group.
Right.
How do I get rid of that? Well, yeah, we'll get to that actually. The other way to change permissions is the absolute mode. I have those octal numbers, and I'm just like, you know what? I know exactly the actual permissions I'm going to set on this file. I'll just give you the straight up absolute values for these things via octal permissions. And so here's an example. I'll list the current directory, and you'll see it's only read, write, execute for the user, but I want to make it wide open. And so I can say, I'm going to actually specify each of these triplets based on their octal permission bits. And so I want all of them to be set. So that's why it's 777. And then if I do a listing, you'll see that they've all been set on this line. Okay, so that's the other way of doing it. Say I want to, instead, I want to only allow group to read and execute, and then I'm going to take out the permissions for other. Then a 750 is basically the binary, the octal represents a binary bit vector that can set the permissions as this is your 7, 111, this is your 5, which is 101, and then the 0 is 0. Okay. Other questions about that? Yeah.
Why is it a discretionary model instead of one of the others like Bell LaPadula?
Oh yeah. Why is it discretionary rather than Bell and LaPadula? I am sure there's a whole lot more history than I know, but this was the easiest thing for them to implement that made it usable for the environments that Unix was initially deployed into. It was easier for and typically these people who were using Unix at the beginning, they were the sort of the higher end users who could subsume, who had the responsibility of securing the machines that they installed. And in fact, on your own Linux virtual machines, you would trust yourself with the security policy. Like you want to be able to configure it rather than have someone else tell you what to do kind of thing. It's in more of the high security environments where you don't trust the users forever, right? I trust me forever on my machine. I'm like the only one using it. But like if you're in the government, and we saw this with the classified documents that Donald Trump took, like that security system has to live beyond the person who created those files. And that's why it can't be discretionary in those contexts. It has to be a system defined thing where that policy is managed by different people over time. Okay, so there are some special settings. There is the --R for recursive changes. I want to make this change all the way down through the subdirectories of wherever I'm currently at. There is this X permission that's associated with the --R because if I specify 777 and the --R, it's going to change all the regular files to have execute permissions. And I only really wanted the execute bit on directories or on binaries. Things that had the user execute bit set, those are the ones that I want to then add execute permissions to on a recursive change. Yep.
Does setting the executable bit on regular files lead to any insecurities?
It's unnecessary in terms of insecurities with the execute bit being set. I don't think so. Yeah, what happens if you have a regular file that's got the execute bit set? Usually nothing. But I don't know. I'll pencil that in. I'll say nothing as not in pen. So this is a common command that you would use to open up every single file within your public HTML tree that has your home directory in without changing the execute bit on like HTML files, right? Those you only need to be readable, but not necessarily executable. And so the X says only the directories get the executable bit set. Okay. The next thing I want to talk about is how do these permissions get set by default? So that goes to your question. There is a command called umask, which will specify the default permissions of any new files that you create. And this is specified as a bitwise complement of the permissions you want the files to have. So this is because it's a mask. It automatically removes execute permissions on regular files because like if you have a umask set for, because when you create a directory, you want the execute bit set, but when you want to create a regular file, you don't want that thing set. And so with your permissions and your umask, it automatically does that for you, so you don't have to think about it. Okay, so if you type umask by itself, you'll get the active umask. And in this case, it's masked to all 0. Don't give anyone any access, which is typically not a umask that you would have. Let's say the umask is wide open, sorry. It's not a mask that you want to have because in any file or directory that you create, is completely wide open if it's all zeros. And so if you set your UMask to be 077, the bitwise complement is 700. This allows only you to access, to read, write, and execute any file that you create by default. And so this is what I do. I can set it to 077. I'll create a directory and I'll create a file in that directory. And then if I do a listing of the directory and the file in it, you can see that the directory has the read, write, and execute bits, which is the bitwise complement here. And then the same thing with the file.txt, but that execute bit is cleared because it's not a, it's a regular file that got created. Yeah.
What's that operation called for the getting the bitwise using actual bits that get the use the complement to like cancel the bits? Like what is
Oh, like an XOR?
it's an XOR? I think?
This is actually, yeah, it's a not operation actually on this one. You're just inverting in this case. Okay, so if I did a UMask 000, then this is completely wide open, right? Everything is set when I create a file. So I'll do the exact same operation using a different directory. And you can see by default, when I create these files, everything's wide open with the execute bit not set for the regular file. Okay, so next we'll get to your question. How do I change the group or the ownership of a file? And that's what chown and change group, change owner and change group are doing. So with change owner and change group, you could also specify the -R flag to do recursive changes throughout a subdirectory. So here's an example. I'm running as root and I touch a file and I do an ls of that file and I have a root owner and a root group set for this file. Change own can actually set both the owner and the group at the same time. So in this case, I separate this with a colon and I say, I want you to change the ownership of this file to be this UID with this group. And then if I do a listing, you can see that this ownership has changed. All right. If I just wanted to change the group, I can just say change group. And so in this case, I say, I want the group ID to be Docker instead of www data. And then you'll see that this changes the group ownership of this. Okay. So are there any questions with that? Yeah.
So you said if you make a folder and you're root of that directory, and then someone creates a file within that, you could not be able to read it. But then as root of the folder, you execute like the chown command and then become.
So you have to be root to change this owner from a root file into someone else. So yeah, the change ownership thing, I don't think I've ever done a change own from any other user except root. Because I don't think you're allowed to just change the ownership from yourself to another user. You can change the group. You can change the group to any other group that you belong to. But I don't think you can change the, like I wouldn't be able to change an owner of a file to any one of you. I don't think. I'm pretty sure not. That would do. Yeah, you know, that Biba, the Biba model, that's what we're talking about here. Yeah, that's what we're talking about here. I guess you could do it that it's allowed, but I don't think you're allowed. The default model, I don't think allows that. Okay. The next thing I want to talk about is privileged access management and the principle of least privileges. So we just got done with permissions and accessing files based on that. So one of the things that you have to consider on a system is that you need mechanisms for controlling elevated privileges. Like there is some trusted code that is going to be able to manage the resources on your box. You need to mediate access to that trusted code. There are two components when we're mediating, when we're doing this operation. The first is the identity management part of this. So you have to be able to strictly identify the users who are allowed elevated privileges. And this is going to be covered later. This is your authentication piece. The other part of this is this access management, privilege access management. And so you want to define the sensitivity of the operations being done and how it can be accessed by regular users. So that's typically called PAM. This is whenever someone uses so security is one of the worst acronym laden fields that I've ever come across, but you'll see PAM solutions out there, or PAM this, PAM that. This is what it means. You'll see PIM solutions, you'll see EDR, you'll see NDR, you'll see XDR, you'll see all these acronyms. And so this is the vocabulary test for this particular thing. So that's why I stuck it in there, privileged access management. So on Linux, by default, the PIM is done using user and group accounts. So things like the root user or the sudoers or the sudo group. And then the PAM is typically done with action-specific permissions like the read, write, and execute, but it can also be done with other mechanisms, which we'll talk about later. If you take the cloud class, you'll see that this privileged access stuff is done completely differently. It's done using a cloud project's identity and access management system, which I'm not going to cover in this class because we have a cloud class that covers that kind of stuff. Whenever you're talking about privileges, you have to talk about the principle of least privilege. And this is just common sense. When you have this principle, any subject that you have allowed privileged access for, you want to make sure they have the minimum amount for them to do whatever job that you want them to do. And that's the principle of least privilege. This ensures confinement of access in case that subject's credentials have been compromised, right? If someone compromises that account, then because you have applied the principle of least privilege, they can only get access to whatever that user had access to, the minimum that that user had access to, rather than, for example, the entire system. So that's important. PAM configuration is a critical component for setting least privileges. This is where it's done. This is where it's enforced in this management policy. And so just to bring this home, this is when it matters. So I'm going to bring up this Uber breach from 2016. Someone compromised a developer account. So, when you do your labs for the cryptography thing, say you found a hash, or actually you can go on the dark web and purchase compromised encapsulation. In fact, Uber got breached last month or 2 months ago again. And the way they got into Uber that time was in the dark web. They were like, hey, I want to purchase a developer account on Uber. How much do I have to pay? And it was like $1,000 or whatever. And so they got access. And so I have a teardown of that one later on in this class. But then this was 2016. And so they got a developer account. It's easy to get developer accounts. And then they use the developer account to poke around. And they see that, oh, there is a CI/CD workflow that's really common in most software dev shops. They have this workflow that uses GitHub, that has GitHub Actions to deploy things in AWS. And so they're poking around as a developer, and they see some developer has hard-coded some AWS credentials. And those AWS credentials, you would have hoped were restricted in some way, that someone had applied the principle of least privileges on those credentials, but they didn't. These were the root credentials for the AWS infrastructure that Uber was using. And this ended up getting them 57 million Uber rider, I guess, the information on all of the Uber customers. And so I put this in here because just last week, the security chief was convicted for covering this breach up. Here's a guy trying to do his job. And as it turns out, he was so fearful of exposing that Uber lost all of the customer data that he paid the hacker to delete the data and then decided not to disclose this. This is high stakes, right? Like your job is on the line, the company's stock price is on the line, and they decided to, rather than, because there's some laws that say, hey, when you get breached, you have to expose that you have to notify. And so instead, they paid the ransom and they didn't disclose. And this turns out, this got this person, well, I don't know, the sentencing hasn't happened, but he was convicted last week. And this is one of the things, this is why cybersecurity professionals are quitting, because you're like, oh God, I either lose my job or I get thrown in jail. But you know, this was actually kind of like, this had not been done before, pay the ransom at this particular point in time. But now this is being done left and right. People are paying the ransoms left and right and not getting thrown in jail for it. Yeah. You don't. So yeah, in fact, so the reason, okay, so here's another side thing. So these criminals are long-lived. And so they're using ransomware software, and they're using affiliates that they actually have a reputation in and of themselves. And so if that crew has a reputation of not doing what they say they were going to do, then they'll lose business that way. And so actually it's a weird economic incentive for the adversaries to actually be truthful in this case, because they have product reliability in mind. They have like customer service in mind for themselves. And if your ransomware victim, which is your customer in this case, is complaining, then yeah, you lose business. It's weird, but like, yeah, you're right. I don't even know. I don't think that data has made it out, but actually what happened here was they tried to pay this off as a bug bounty. So then they like had the person who did this register for like the bug bounty, and then they paid, like they gave this reward as a bug bounty thing, and then they tried to say, yeah, and then they trusted that person to delete the data. That was all found to be illegal. So that's where this verdict just came in last week. So I put it in there. Yeah.
So you mentioned there was something about like AWS credentials in like, I don't know, like plain text or something like that in their repo. So you're saying like if the credentials hadn't been root, it would have been
Better. Yeah.
Better, like just less.
Less. Yeah.
But wouldn't the step to just not have it be in plain text at all?
So right now, GitHub, anytime you push something that looks like a credential, they'll say, get rid of this in the source code. Yeah. The credential does have to show up somewhere, decrypted, like in memory, for example. And so you can't get rid of the fact that I need to present a credential to AWS, because AWS is trying to remotely authenticate my access to their system. They need something. And typically it boils down to a single factor, that key that you have to keep secret. Now, if an adversary is on the box that is using that key is probably going to get exposed sooner or later. It might not be viewing the source code, but it could be opening up memory or trying to find it in environment variables or these sorts of things. Yeah.
You use like a third-party key management?
Yeah. So if you're taking the cloud class, there's this secrets manager thing. And then in AWS, it's called KMS, Key Management System, that will automatically manage all your secrets and then rotate them. Because you do need, like, if a key does get exposed, you want to be able to rotate it just like that. And so instant rotation of keys is a service that cloud vendors will sell you. That's actually a value add. I don't know how much they're charging for it. So you'd have to like, they're charging me 10K a month to rotate my keys. I would be like, no, thank you. I'll just write a Python script to do something or other. But like, yeah, that's one of the things. Secrets management is a big thing because we have secrets everywhere now with the way we're integrating with a bunch of APIs and different services. And so that is a thing. Yep.
Isn't that specification like oftentimes just done through like PGP?
Authentication is when you are authenticating software with services, it's always done with a single key. It's single factor by definition, and it's usually one key that rules it all. This is a problem, but it's going to be hard to fix this, right? It's different when it's users, right? With users, you can do a multi-factor thing. With actual account keys, the only other factor you can use is the IP address. Like if you can bind a secret to an IP address, you can reduce the attack surface by saying if someone steals that key, they can't use it on any other IP address other than the machine that it was intended for. And this is how, like if you take the cloud security class, this is how AWS fixed the problem with the Capital One breach. It's like people are stealing credentials like this and using them everywhere else. And you would want to use either the IP address or the geographic location information of where the access came from to do an extra step of authentication rather than just the secret itself. So that's an emerging thing that people are working on. Okay, so some examples that are specific to Linux. So that was a cloud example. But here's a problem. You have ping, and this command just checks to see if a remote host is live. It turns out in order to implement this command, you need root privileges. The reason why you need root privileges is because you're crafting a raw packet and sending it over the network. And Linux doesn't want you to do that unless you're the administrator. And so it initially was giving ping full root access to be able to do this particular operation. The problem is that if somebody has misprogrammed ping and there is a vulnerability inside ping, exploiting ping gets you full root access to the system. We say that ping is not confined in this way because it's running as root. And as soon as you get code execution on ping, like say it has a vulnerability that leads to code execution, the privileges aren't confined because it's got root effectively. You need to do something to reduce the privileges on ping. And that's something that we'll talk about later on in this class. How do you do that? Here's another one that all of you probably have done. It's like you're installing Python packages left and right for your Python program, but the packages themselves will run at the privilege level of the person installing it, right? Because you're going to install that package as you, the user. If there's a bug in that package, or if it's a malicious package, then they have access to whatever your user account has access to. And if you've installed that package on the root, sort of the system Python, then again, they have complete root access to your machine, and it's not confined in this case. So this is a thing, and this is one way adversaries are trying to get into systems. I'll put a whole bunch of packages up on PyPy, and someone's gonna pip install that thing. Especially, if I just do like, maybe my thing does left tab or left padding, and some lazy developer doesn't want to implement left pad by themselves, they'll be like, oh, look at this Python package, it does it for me, and I'll pip install it. And it will implement that function, right? Like adversaries aren't completely dumb. They'll like, oh yeah, I'll do whatever it takes to make it look kind of useful, but then I'll slide in something else, and then I'll put up a web page that says, hey, look at my thing, it works. You'll install it, it works, and then there'll be something underneath. So that's a thing now. When you are on a system and you're doing access control, one of the things that you will need to do is manage privileges and escalating them and de-escalating them. And so on Linux, the basic privileges are associated with the UID. So every process is labeled and tagged with a UID. And this process inherits the UID from a parent process. So if I have a root process and I have that root process create another process, fork another process, that second process also has a root UID. So that's the way it works. You inherit the UID. Every file is also labeled and tagged with that UID, and that's what the ownership one thing was that change own was doing. And a file, if a process creates a file, the file's owner inherits the UID from the process that created it. So that's how we create files and have UIDs on those files. The privileged process has a UID of 0, and this special UID has the property that it can set its own UID to something else. And that's with this set UID system call. The root process can speak for any other user on that system or act as any other user on that system. Okay, so one of the reasons that you need the root process to do this is because when a user logs in, you don't want that user to be running at the root privilege level. So you need to be able to reduce or change the UID from the root process to something lower or something different. Okay, so this is how it works. How the set UID function works to de-escalate privileges. So we're going to talk about de-escalation first, and then we're going to talk about escalation second. So this is how de-escalation works, and the typical example to use is the login process. The login process has to run as root because it's going to be the one to take the input from the keyboard, the username and password, and it's going to have to open up Etsy password, open up Etsy shadow, do the validation of the password hashes without revealing the password hashes of anyone else, and then change that process to execute a shell for the user that has logged in. So this is how it typically works. So in green, you have the root user running this login process. And then you have a regular user in red, Alice. And this regular user has a UID of 1,000. And the regular user is going to enter the credentials into the login program. The login program is going to validate the username and password combination. And then the login program is going to fork, assuming the login is actually valid. Then what the login process is going to do, it's going to fork itself, and then it's going to set its own UID, the forked process, to the user. So it has to de-escalate the privileges on this forked process, and then it executes the user's shell out of Etsy password. And then that's how the user now has a UID of 1,000 running the shell with UID 1,000. Okay. This shell can be used by Alice to launch any other tools, but all of those other tools are being launched with the UID of 1,000, right? Because now the parent, the shell, which is now the parent process for any of the commands Alice runs, the parent has a UID of 1,000, so all of the children will have UIDs of 1,000. This is done throughout the Linux process tree. You have this special function that runs as root, has a PID of 1, the very first one. And this is crafted by the kernel and then run. And then from this init process will go through and launch all of the startup programs for Linux. And so so it'll be sitting there forking off all the system services. And so it'll be forking off things like the get terminal, like the login stuff, or maybe it's a DNS server or whatever you have configured to start up, that gets spawned in this init process stuff. And all of these also run as root. And then from here, the login process is running as root. And from here, based on authenticating a user and then de-escalating the privileges, eventually you'll get down to a process down here, like bin shell. And from there, these are the user processes at the bottom. And so for this particular user, all of these programs run under this user's UID. When you exit, eventually the init process will reap the orphan process and clean up. So that's basically, if you do a PS tree, which you've done in one of your labs, you should see something that looks like this, logically. Okay, so we talked about the shell a lot. So what is this? It's just basically a command line prompt that in a tight loop gets a command from a terminal, reads a line of terminal text, and then forks a process, a duplicate of itself, and then performs an exec on the string that the get command returned. And that's all it does. This is what it looks like. So it gets a command. And then this is from your CS201 stuff. It forks an identical copy of itself. The child will turn around and execute whatever that command was. And then the parent will basically wait for this child so this is in the foreground. It's going to sit there and wait for the child to complete. Or if you put it in the background, or the process returns, then it basically goes back into the infinite loop. So this is logically what's going on in your shell. And this is all being invoked. This fork is basically creating an identical copy of the parent process with an identical UID. Okay. So let's talk about creating files. So after login, so Alice goes through this login thing, invokes a tool using her UID, so another fork of the shell, and then an exec on this tool. And say this tool does a create file. So it opens a file, does a write to it, and then does a close. The owner, because the UID is inherited on the files that this process creates, the owner is now 1000. And then let's say that Bob comes in with his UID of 2000, does the exact same login, and tries to open this file and read it. The question to ask is, should this work? Should Bob's process be able to open this file foo? And based on our previous conversation, this depends on what Alice has set as her discretionary access control policy. And this is where the change mod and the UMask come in. Alice can allow this access if, for example, she has other access, other read access enabled for this particular file in her UMask. Okay. So this, the security reference monitor in the kernel is basically going to enforce Alice's policy to determine whether Bob's process has access to that particular file. Okay. So the question is, why does login need to run as root? And we actually talked about this earlier. It basically needs to check those username password entries and especially access Etsy shadow so that no one else can access it except for the login process. And then it also needs to de-escalate the shell from root to another UID, to the user's UID. So those are the two reasons that the login process runs as root in this case. So that's the easy case. Shedding privileges is an easy thing to do. What about controlling how regular users elevate their privileges? Because eventually you do want to do elevated operations that required elevated access for regular users. And to give you an example, there's this really famous example from 1974, which basically articulates the need for escalating privileges in a controlled way. And this is this Mu accounting problem. And so you have a multiplayer game called Mu, and you want to maintain a high score file across all of the players of this game. So you have these different game clients that are being run by different users. So UID X and UID Y are executing this game client. And you want to maintain this high score file in the middle. So should these players be able to update that high score file? Yeah. So yeah, the UID X and UID Y need to be able to write into that high score file. So that's yes. And so maybe you allow that. You're like, okay, I'll get the game client to just access the high score file and then report the high scores. But do we trust the users to write the file directly is the question. And I was like, of course you don't. Like, I've played enough video games to have come across cheaters. And yeah, you would just say, no, I'm just going to lie and just write whatever I want to. So one of the common ways to solve this problem is to use a trusted third party, right, in security. And so you can have a trusted process. And only that trusted process is going to update this high score file. And then in this case, oh, well, I'm going to mediate the update to this file. And so they're going to report their scores to me. And then I'm going to write this to a file. But is this good enough? Like, does that solve the problem at all? No. So already I see some of them are like, no, that doesn't work at all. And so no, because you just lie to the score server, right? Like there's no integrity here. So it's like, okay, well, I'll just lie to the score server. So you need to do something else. You need to ensure that the score was computed correctly. And this is where the setuid programs came about. So setuid is not only a mechanism for de-escalating your privileges from the root process, it is also a way of elevating or changing your UID to other UIDs in a controlled way. And this controlled way is basically allowing a program to act as a security reference monitor, a custom reference monitor for any of the resources it needs to access. So much like Linux, the Linux kernel is a reference monitor for accessing files. You can have a setuid program as a reference monitor for modifications to any of the files that it owns or that its owner owns. So that's the idea of setuid programs. Yeah. Yeah. So is this something that gets hijacked? You bet. Yep. Yeah. This is why this is hard to get right. And there have been multiple iterations. So now it's done pretty well. But yeah, we'll talk about where this goes wrong. Okay, so the setuid facility allows a user access to the owner's privileges, but only in the manner permitted by the owner's program. I'm going to write a program as myself, and then it's going to do something very specific, but I'm going to allow you to access this program and act as my user ID to do those operations. And if I've done it correctly, if I trust myself to not have any bugs in my program, then this will all work, right? And it'll be secure. But I wouldn't trust myself to write a setuid program for myself, but I would trust other people with many eyes to do this for other programs. But the idea is that I am going to mediate the access to my resources. And in this case, the game client is going to mediate access to the high score server, the high score file. Okay, so how does this setuid facility solve this problem? So in this case, I'm going to have this game client, this game executable, and this high score file owned by root. But this game client is going to be, because the game client is owned by root, a regular user is not going to be able to modify it. And so that's the idea. I'm going to allow users, regular users with different UIDs, to do a setuid operation to run this game client as root. And assuming there are no bugs in this game client, I am then going to trust that the update to the high score is done in a controlled way through the game client code itself. And so I'll fork and exec this game client, and it will set UID to root and then update this high score as root. And then I won't have this problem where the UID X or UID Y is faking their score into the high score file. Okay, and this could be, it doesn't have to be done as root. It could be done as any user who wants to mediate this access, or yourself, for example. Okay. This is a form of trustworthy computing because you're trusting that the game client code is going to act faithfully in the way you expect. And then the elevated privilege access is going to be done through the game client code correctly. Okay. The fact that this game client is owned by root ensures code integrity, right? I don't allow UID X or UID Y to modify that game client. So the writable bit on the group and the other better be turned off for this set UID program is the idea. Yep.
Yeah, basically the user has execute access, but not execute read access, but not write.
That's exactly it. The user has execute and read, but not write. If you have a set UID program that is writable by group or other, you're in trouble. Unless that, I don't know if I've ever seen one of those. Definitely not other writable, right? Because then you just might as well have given up your password. So yeah, that's the idea. Okay, so now I'm going to do the full privileges example. So you have a login process running as root. The user logs in. The login process is going to have to read the credentials and check it against etc shadow. And so that's why it runs as root. If it's correct, it will, well, one of the things it does is it reads the UID, the GID, the home directory, and shell. And then so it goes into this file and gets all that information. And then if it's correct, it calls that set UID to drop the root privileges to run as Bob. It calls the change directory to change into Bob's home directory, and then it executes Bob's shell program, and then it runs as Bob as the next step. And then Bob has this login prompt where the shell is running as Bob's UID. And then let's say after login, Bob wants to change his password in etc shadow. So like for your Kali VM, when you go and you change the password, you want to run the password program, and that password program has to run with elevated privileges because it needs to access etc shadow, but you don't want Bob to read etc shadow. So you have to mediate Bob's access as root using the password command. And so the password command is a set UID binary. So it forks an exec's password containing trusted code. So password is now trusted. And this trusted code is going to read Bob's password hash to authenticate Bob. And so in this case, this is the entry. And so here, not even Bob sees this hash, right? Because Bob doesn't have access to etc shadow to read it. This is being done through password. And this is what his password hash looks like. And let's say I try and change my password. Now, when password goes to change this, the access through etc shadow is done through password. And so again, Bob doesn't have direct access to this. The access is done through the password program, and this stuff can get updated without Bob seeing anyone else's entry in this etc shadow file. So even though he's modified the file, he hasn't read any other parts of it, and he hasn't changed any other parts of the file. And this is the Mu accounting program, right? I am mediating the access to that file. Yep.
So password is like trusted code, but what part of the architecture is preventing that password command from getting hooked?
Oh yeah, yeah. So yeah. Let me. Well, first, let me say. Let me talk about. Well, how do I get this? How do I configure password to do this? How do I create that set UID program? So when I said there were only 3 permission bits, I lied, and I lied again when I said it was a sticky bit. There's also a set UID permission bit associated with this. And so someone has to tag the password binary with this special set UID permission bit that allows anyone who is able to execute that program to also set the UID to the owner. So it's a special thing. Not only can you execute, but you're allowed to change your UID to whoever owns the program. And so if this bit is set, that's what happens. And in this case, the program owner has to be careful because you're letting anyone execute this code that you have specified with this bit to run as you, have full access as you. And so if there are any bugs that allow code execution, they got your account. They can win. Okay, so this is the mechanism. This is how, like, say I compile the password binary. It's a C program that does all of this for me. Then I change the ownership to root, and then I set the set UID user bit. So I want the user who executes this to be able to set the UID to be whoever the owner is, and in this case, root. So when I execute this, when I do an ls-l of this binary, you'll see this set UID bit set. So a little s means that it's both executable and set UID at the same time. That's how they encode it without adding a whole bunch of other bit fields across it. You notice that the T replaced the little x. So any of these bits, they overload these positions with the labeling. So a small s indicates it's executable and set UID. And if you look at the permission bits, anyone can read and execute this program. So group other readable and executable means everyone on the system can execute. And then moreover, upon execution, because it's the user set UID bit that's set, you run this program as root in this case. So this basically enables applications like ping and password that need the root level access to elevate the privileges for the duration of their execution, but to be able to be invoked by a regular user. So the regular user is accessing these privileges in a controlled way, is what's going on. So how can you tamper with this? It turns out there's a whole bunch of different ways you can attack this thing, and they had to incrementally shut all these things down. Like say I run the password program, and then I try and do a GDB attach, like a debugger attach. And I think this is like in the malware class, this is one of the things that you would do, attach to a program that's running to try and dump all of its memory. How do I prevent that, right? Like if password has memory mapped etc shadow into its process space, and somebody attaches a debugger to it, then you read all those entries anyway. So ptrace, ptrace is another facility for attaching as a debugger and controlling that process. Ptrace and GDB, they're disabled on set UID binaries. In addition, what happens if you add to the load library path of password? Say password needs libc, and then you put a rogue libc in the file system and try and get password to load that so you can intercept all of the reads and the writes going to and from path like ltrace kind of thing. And well, I think we did this in 201. That's like the first ltrace binary. How do you prevent ltrace password from revealing the entries going back and forth between the password binary and the file system? So changes to the LD library path and LD preload are disallowed on set UID binaries. And they used to be allowed until people were like, oh, wait, I can completely hijack a set UID binary, and now they're disallowed. And then the bit is ignored on shell scripts because shell scripts are too easy to edit and do bad things with. So they just disable it. I'm going to briefly mention the set GID bit. So we talked about elevating privileges as a user. You can also allow group elevation. So if I want to temporarily allow you access as a particular group, then I can set this group bit. And it works similarly, but it's not prevalent enough for me to actually talk about. But just to know that that set UID bit could be associated with the group. Okay, when you run a set UID program, there are multiple UIDs that you have to deal with now. You have the original UID of the user, and then you have the effective UID if that user has been able to set UID as a different user. And so in this case, the real UID, or RUID in a process, is the owner of the process, the user who created the process or inherited from the parent process. And this is what you get back when you do the get UID system call in C. There's also an effective user ID. So if you are allowed to elevate your privilege level, you're going to be acting as a different user with elevated privileges, and that's what the effective user ID or EUID is. And this determines your access rights. And this is important. So you can get access to both of these things by doing a process listing. So in this case, I have I list this binary, and then I execute this, and say I'm executing this as myself. If in a different terminal, I do a process listing, and I do a process listing that says, well, what is the effective user and the real user? Within this process, the effective user, the rights that I have is root, but the real user is kept track of. Because if I create a file as part of the set UID binary, I need to be able to create it as the real user rather than the effective user. I don't want the execution of this file necessarily to create more files owned by root. And so this is by default. When you create a file that's mediated by the set UID binary, you create it as the real user. Okay. So here is another exam question on a Linux I think this is a Linux certification question. I have this listing. It's got some permissions. It has owners and it has groups. And the file name is all the way on the right. And let's say Alice is a member of her own group and then the pcrack group. And then Dave is a member of his own group and this gdev group. If you look at this file listing, which files can Alice write? Let me take a look at that. The bottom one?
Or the bottom four.
The bottom four. Well, definitely the setup file. Right, actually. So, yeah. So definitely the setup file, right? Like she's the owner and it's user writable.
GData is wide open.
GData is wide open, so has access to write that one. And hosts. Yep.
Yeah,
Yeah.
it is.
So setup, source G, and hosts. Because, so this is because it's, this is, wait. Oh, this is other, so this is actually incorrect. Which,
There are others.
oh, wait, but this is the sticky bit.
Okay.
Sorry. This is correct. The sticky bit. Yeah, so the sticky bit makes GData not. So then it's the setup one because she owns it. Source G because yeah, she owns that. And then the hosts because it is writable by the pcrack group, which she's a part of. Okay, let's hope I do better this time. Can Alice execute gtool? Yep. So that's what this little x allows here. So that's yes, other plus x. And then the last one, what are the real UIDs and the effective UIDs of gtool when run by Alice? Yep. So RUID of Alice, what about the EUID?
Oh,
EUID of Dave, because it's the set UID bit. So you set UID as the user in this case. Okay. Any more questions about this? So we're next going to talk about sudo. And when I talk about sudo, the obligatory XKCD has to come up. So this is the XKCD cartoon, make me a sandwich. And it's like, heck no, make it yourself. And then sudo, make me a sandwich. And it's like, yeah, I'll do that for you. That's basically what's happening here. Sudo is attempt to execute a command as root. And typically it's a command that the system doesn't want to do for you unless you are root. So that's why this cartoon is kind of hilarious because I've done this so many times. It's like, do this operation. I'm like, no. And then sudo, and I'm like, yep. So sudo allows you to execute a command as root, but it's done on a specified policy. Before we had sudo, we just did an SU and then did all of our operations as a root user. Like if we had the root password, this is like shared system administration, which actually is still a thing these days. You're like, here's the root password for this box over here. And then you have a collection of 4 or 5 trusted administrators. And then that's how you do. You just SU and then do all the operations. And you're like, well, everyone can basically own everything on that box, even though, maybe I just wanted this administrator to do backups, right? Like if your job is only to back up the file system, I shouldn't give you like the complete root privileges. And so sudo was a way to try and mediate the access, to actually do some compartmentalization of the privileges, to do a least privileges operation on the root account. And so now this is everywhere to support least privileges operation. So if you look at sudo, it's owned by root and has that set UID bit set. So when you are running sudo, you're going to elevate your privileges temporarily as root when you do that command. So that's what it looks like. So this is an example of using it. So the user logs in and then runs sudo. What sudo will do is, say you're going to say sudo tool. I want to run that tool, but I want the effective UID of me running that tool to be root. And that's why I'll do sudo tool. And then sudo will first check your authorization level to act as a super user. And sudo has an access control mechanism that's separate from what we just talked about with Linux's default, right? They have to build something on top of that to access this one command. And it's a good modification. It checks to see if this user is able to run sudo. And then if so, we'll set the UID to 0, fork the tool, fork the process and execute the tool. And now Alice is running this tool with root privileges. Okay. So we talked about wanting to enforce least privileges. It's really important to configure sudo to control access to who gets to execute it. So you want to control which users can run which commands on which machines at which level of user and group access, if you want to restrict how the users and groups work on a sudo command, and using what level of authentication. Do I require a password authentication step to run a sudo command is what this thing refers to. And so this is all configured with this etc sudoers file. And this is basically a common PAM solution for Linux. And it's a PAM solution that's built on top of the regular Linux PAM. There are many plugins for managing this particular command that you can basically import. But I'll just talk about the default ones. So in this file, it has a special syntax. On every line, you first specify the username to grant access to the sudo command, whether or not you will want to allow a particular user access. And then if so, you're going to define the rest of this to be what kind of access do I want to give this user. And then I'm going to say, well, which hosts is this user allowed to run sudo on? And so this, in this particular case, we're thinking about multi-host systems where you have a master sudoers file that you push out to all of the machines. And then all of the machines know their own name. And then based on this file, we'll mediate access. So in this case, this particular username's got access to everything. And then in parentheses, you'll say, well, what set UID users does this particular username have access to run as? So this is your users part. And then what groups, set UID groups, will this user be able to elevate as? So that's the next two. And then finally, which commands will this user be permitted to run? So in that case where you have a system administrator who's only doing backups, you're like, okay, I'm going to put this in the sudoer line that you have sudo access to rsync this one command to do the backup, and that's it. And then I have restricted that user's access so that they can't wipe the whole system out. They can only rsync in this case. Okay, so here's an example. So in this case, this is wide open. This is the root account on any host can run as any user, any group, and any command. So this is basically what root does anyway. So it's like this is like a no-op. But here's one. So this particular user on any machine can run as root this command and this command only. So if I do a sudo, the only thing I can run is this cat etc shadow is the only command I can run. And you can see how that compartmentalizes my access, right? I can't do anything crazy as root. I can only run one command. I can expose the password hashes, which is something, but at least I've restricted that. This prevents me from viewing any of the other files that root has access to, right? So this is a pretty good least privileges example. And so, for example, well, I can't read anything else in /etc unless I'm explicitly allowed to. One of the things that you've seen, if you run sudo on a Linux lab machine, which some people accidentally do, like lots of people accidentally, I've done that myself. Those unsuccessful attempts are typically logged in the operating system in this log file. And we'll get familiar with this log file later on in this class. Here's another example. Anyone in the group wheel on any machine can run as the root user that file. So exact same thing, but exposed to anyone who is part of the wheel group in Etsy group. Here's another one. I want the web admin on all machines to be able to run as root without a password being supplied, the web server, right? Like this web server needs to run all the time. And as long as any web administrator can basically start the web server if it has crashed. So that's useful. You can do fancy things like specify the IP addresses that are allowed for particular accounts. So in this case, say all my web servers are on this /24 subnet, then I can say only the web admin on these IP addresses that my web servers are running on can run that particular web server to really reduce the privileges. Okay, are there any questions about sudo and sudoers? Yeah. The wheel is a trusted group of administrators typically. It used to be a lot of the system processes belong to the wheel group. And then you would have one group to manage all systems-ish services and things. That has been my experience with the wheel group. I don't know where it came from though. Yeah, but you do see wheel everywhere on Linux systems. Well, less so now than before, but you used to see wheel all the time. But I actually don't know. I don't know the origins of that actually. That would be a good thing to post on Slack if you decide, if curiosity gets a hold of you and you have to know. Yeah, post that on Slack for me to know too. Okay, I'm going to talk about some meta issues when it comes to privileges. One of the biggest problems with an approach like Etsy sudoers is that you have a whole bunch of standing privileges that are encoded in that file that anyone can get access to. And so there was this report that was released last year that talks about how most of the data breaches involve some kind of privileged account and standing privileges, where those privileges are just associated with the account forever. And if you get access to that account, you can break the bank with it. And so people are talking about, and this is within the last year or two, an idea of zero standing privilege, where you're going to take all the privileges out of all your endpoints and then dynamically issue them back on demand. So this is a dynamic, context-aware, time-limited privilege activation for an endpoint. And that's basically centrally managed, where you can have in that central endpoint, you can be operationally aware and you can tune the privilege access dynamically. So that's the idea of zero standing privilege. So this is an example solution. I got this out of a data sheet from one of these vendors. So here are all your endpoints on the right. And rather than encode everything in Etsy sudoers, you're basically going to remove all of that stuff. And then when someone needs that access, you can basically centrally either issue a 2FA, like say, you could either, based on the location that this connection is coming from, you can do some situational awareness before enabling access. And when you decide to enable access, this is pushed out temporarily to that endpoint and then removed after that time expires. So this gives you visibility in one place to all of the privilege operations that are happening across your entire fleet. So that's the idea. And then, so this SIM and LDAP thing, these are basically big data stores. This is the authentication piece, and this is your big data store. And so the authentication piece is needed to say, hey, I want to make sure a human that I trust is initiating this command. And then I want to make sure that all of the privileged access is logged down here. Okay. Another issue is that we have these privileges per UID, and this is much too coarse. So this is the idea of installing a Python package, and that package has access to you and all of the things that you have access to. And so you don't want that. So for example, you want the password program to only have access to Etsy Shadow, but like the password, because it runs as root, if it's got that bug, it can basically do anything as root. And so there's a lot of ways you can address this. And we'll cover some of these later. One way is to use virtualization, confinement, and isolation to try and keep the detonation point from going beyond a certain area. That's what these things do. Another thing to do is to try and remove from the password binary certain system calls. So like, does the password binary need to invoke a fork or an exec? You know, that could be something that you could control. The next thing which got implemented in Linux is capabilities. And so that's what the next thing is. And so Linux has a whole bunch of different access control things. This is one thing that got added per file to try and get much finer granularity on the level of access that a particular binary has. Rather than taking on the privileges of the owner, you specify what capabilities in the system that particular file has access to. And then this is done on a per program basis, and it's done on a per operation basis. So it's much finer grained. So here are some common capabilities that you could assign to a program. One is a capability to send signals to other processes. Another is the capability to send raw packets, which is what ping needed, right? Ping ran as root, but it only needed root because it just needed to send raw packets. So we're going to fix that with Linux capabilities. So that's how we're going to fix this. And we're going to fix this using two commands. There's this get cap to examine file capabilities and a set cap to set them. And so if I do a get cap of user bin ping, you can see that it's got this capability to send raw packets. And as a result of that capability, it no longer needs set UID. So you can run this command, and because this capability has been set for this program, it no longer needs to run at root. Basically, this runs at the user ID. Oh, sorry, I have a different listing here. Shoot. So if I did an ls-al, you would see that ping doesn't have the set UID thing set. Sorry about that. That's the wrong animation. I listed a different file. Okay. If you wanted to set the capabilities of a file, you can use set cap. So in this case, I can do a set cap and I say enable raw sockets and promiscuous mode, which is capnet admin on TCP dump. And then you can see that when I do a get cap on TCP dump, it's got those privileges. Okay. And so I'm going to end with that word about Android. It's Linux underneath, and it does confinement based on user ID. And it's got a permission model on top of that for capabilities. And you've seen this on your device. It wants access to your location or notifications or those sorts of things. Those are things that are done as capabilities, but underneath it's using user IDs as confinement. And that's where I'll end. All right.